Okay, I forgot to mention in the previous video. Okay, so we talk about the surface integral for a scalar function. Okay, if you guys still remember, on line integral we talk about the piecewise curve. Okay, same goes to what we have in the line integral. We also have a theorem for piecewise smooth surface. Means that instead of we have a surface at one place, we also can have a piecewise smooth surface. Means that we kind of uh, we have two surface that connecting to each other. Okay, so for example this question, okay, they give you the scalar function, and then they say that the surface is the portion of the curved surface of the cylinder y squared plus z squared equal to 1 in the first octant between x equal to 0 and x equal to 2, together with the portion of the plane to z plus y equal to 2 for y between -2 up to 0 and for z between 0 up to 1. Okay, so from here actually, if we sketch it, you will get like this. Okay, at this side is actually referring for the first projection, I would say. No, it's not first projection. You should say first surface. Okay, and then for this statement, okay, like let me, okay, it's for here. Okay, and then if you notice that we have another surface that is attached together with the first surface, which is in this part. Okay, on the left side of y actually. Okay, so this one is actually come from the statement together with the portion of the plane 2z plus y equal to 2 for y between -2 equal to 0 and for z between 0 up to 1. So eventually you have two smooth curve that is attached together that will be considered as piecewise smooth surface. Okay, so the idea is similar to what we have learned on line integral. So we're going to solve for every surface involved and then put together. Means that you find the summation for the surface integral for both surface. Okay, so if you see, let's talk about the first projection. Okay, so for this part, when it's only involved for the first octant, so we have the blue colors here. Okay, so eventually you will see that this is, sorry, let me change the color so that you won't be confused here. If you see the projection on xy plane is actually for this part. Okay, so if we like to sketch, it actually involved for this part with x and then y. This one is for the first surface. This one is 1, this one is 2. Okay, so we know that for the first one is actually come from the y squared plus z squared equal to 1. Okay, so from here, let's make it z as a subject. So you will have square root 1 minus y squared here. So this will be used for you to find ds. Okay, so from here, ds. Okay, so from here, if you see that ds is equal to square root, our fx is equal to 0, right? Because there is no x here. Okay, and then we have fx fy squared plus 1 here. Okay, so we have dA here. Okay, so since we know that fx is equal to 0, and then for y, if you differentiate this one respect to y, so eventually you will get y squared divided by 1 minus y squared here. Okay, and then plus 1 dA. Okay, so if you modify this one, actually you will get that 1 equal to 1 divided by square root 1 minus y squared. Okay, let me clean so that will be clear enough here. So here you will get that 1 over, if you simplify this one, you will actually get in this form, dA here. Okay, so you will use this part to be substituted into the original question. So the given question just now, let's solve for the surface, the first surface, x y squared z ds just now. Okay, and then we have, okay, you got no problems to solve or to get the limit because it's just a square, means that the limit for both x and y is a constant. Okay, so from here, if you notice that we have set here, okay, back then, since we have changed ds into dA, so obviously that it will only involve for x and y. So you have to change z here. So z is actually from here that you have modified. Okay, so from here you will get that x y squared. So our z just now is equal to square root 1 minus y squared, and then our ds is equal to this part, so it's equal to square root 1 minus y squared dA. So this one can be cancelled out with this one, so that's why you will get x y squared dA. Okay, so since it's involved with a rectangular shape, so obviously that you will get the limit for 0 up to 2, for 0 up to 1, x y squared dy dx. If I change to if I choose to use dA as dy dx, you can also use dx dy. It should be no problem at all. You will get this part as 2 over 3 like I give to you here. Okay, but then how about for the second surface? Okay, so I would like you to figure out by your own for the second surface, which is on the that involved for the plane 2z plus y equal to 2 just now. Okay, so I'd like you to figure out, okay, for the second part, okay, and then finally you put it together, you will get that the surface integral for the given question should be, okay, so the given question here is x z ds is equal to the summation for surface 1 plus the summation for surface 2. So this one have been shown for the first surface. What about the second surface? Okay, I have shown to you also the final answer here that you can compare. Okay, so the idea is similar to what I have explained in the previous video. Okay, same goes to here. Okay, you have just to grab the idea on how can you get the ds for the second surface and also the correct limit based on the condition given in the question. Okay, so that is when we are talking about piecewise smooth surface. Okay, so now let's move to the